Question 1. Implementation of MPLS VPNs requires careful consideration of routing isolation and security. Which of the following approaches best ensures the secure and efficient separation of customer traffic within an MPLS network? Option A. Disabling all ingress and egress filtering on PE routers for VPN traffic to maximize network flexibility. Option B. Assigning identical route distinguisher RD and route target RT values to all VPNs to simplify management. Option C. Utilizing virtual routing and forwarding VRF instances on provider edge P routers, coupled with appropriate route distinguisher RD and route target RT configurations, and implementing ingress/egress filtering. Option D. Configuring static routes within the MPLS core to direct traffic between customer sites. The correct answer is C. Utilizing virtual routing and forwarding VRF instances on provider edge P routers, coupled with appropriate route distinguisher RD and route target RT configurations, and implementing ingress/egress filtering. Explanation. Scenario analysis. Implementing MPLS VPNs in a large enterprise network presents significant challenges due to the complexity of routing, security, and service level agreement (SLA) adherence. Network engineers must balance performance optimization with robust security measures to prevent unauthorized access and data leakage between customer sites, ensuring consistent service delivery across diverse network segments, and maintaining compliance with internal security policies and potentially industry-specific regulations, if applicable to the exam's implied jurisdiction, requires meticulous planning and configuration. The potential for misconfiguration leading to service disruption or security breaches necessitates a rigorous approach to best practices. Correct approach analysis. The correct approach emphasizes a layered security model and strict adherence to RFC standards for MPLS VPNs, specifically focusing on the separation of customer routing information through VRFs and the use of BGP extensions, like route distinguishers and route targets, for isolation. This aligns with best practices for network segmentation and traffic engineering, ensuring that each VPN's routing table is independent and inaccessible to other VPNs. Utilizing MPLS labels for forwarding traffic provides a secure and efficient mechanism for transporting customer data across the provider's network without exposing customer IP addresses or routing information. This method directly addresses the need for security and isolation, which are paramount in multi-tenant or multi-customer environments, and is consistent with the principles of secure network design as generally understood within telecommunications frameworks. Incorrect approaches analysis. One incorrect approach involves relying solely on static routing within the MPLS core to direct traffic between VPN sites. This fails to leverage the dynamic routing capabilities of BGP and MPLS, leading to scalability issues and a lack of inherent security. Static routes do not provide the necessary mechanisms for VRF isolation, making it easy for traffic from one VPN to inadvertently reach another, violating security and privacy requirements. This approach is ethically problematic as it compromises the integrity and confidentiality of customer data. Another incorrect approach is to disable all ingress and egress filtering on the PE routers for VPN traffic. This would allow any traffic to enter or leave a VPN, regardless of its source or destination, creating significant security vulnerabilities. Without proper filtering, malicious traffic could be injected into a VPN, or sensitive data could be exfiltrated. This directly contravenes the principle of least privilege and is a clear ethical failure in protecting customer data and network integrity. A third incorrect approach is to use the same route distinguisher, RD, and route target, RT values for all VPNs. This would effectively merge the routing tables of different VPNs, eliminating the isolation that VRFs are designed to provide. Traffic intended for one VPN could be misrouted to another, leading to service disruption and a severe security breach. This approach is fundamentally flawed in its understanding of MPLS VPN architecture and represents a critical failure in implementing secure and functional VPN services. Professional reasoning. Professionals should approach MPLS VPN implementation by first thoroughly understanding the specific requirements of each VPN, including security policies, traffic patterns, and SLA objectives. They should then design the VPN topology using established RFC guidelines, prioritizing VRF-based isolation and appropriate BGP extensions. Configuration should be meticulously reviewed, with a strong emphasis on implementing ingress and egress filtering on PE routers to enforce security policies. Regular auditing and testing of the VPN implementation are crucial to ensure ongoing security and performance. This systematic and standards-based approach minimizes the risk of errors and ensures the delivery of secure and reliable services. Question 2. Cost-benefit analysis shows that implementing an Alcatel Lucent MPLS solution for enhanced traffic engineering and service differentiation is a strategic imperative. However, the proposed solutions vary significantly in their initial capital outlay, feature sets, and projected operational complexity. Which approach best aligns with professional best practices for network deployment within a regulated telecommunications environment? Option A. Choose the solution that demonstrates a clear alignment with defined business objectives, offers a justifiable return on investment considering both capital and operational expenditures, and has a well-documented path for compliance with relevant service provider regulations and industry best practices. Option B. Select the solution that offers the most comprehensive feature set and highest performance metrics, assuming that advanced capabilities will future-proof the network and justify any increased initial investment and operational complexity. Option C. Prioritize the solution with the lowest initial capital expenditure, even if it means compromising on certain advanced features or requiring more extensive manual configuration and ongoing maintenance. Option D. Opt for a solution that leverages the latest proprietary Alcatel Lucent technologies, focusing on vendor-specific advantages without a thorough evaluation of interoperability, long-term supportability, or the total cost of ownership beyond the initial purchase price. The correct answer is B. Select the solution that offers the most comprehensive feature set and highest performance metrics, assuming that advanced capabilities will future-proof the network and justify any increased initial investment and operational complexity. Explanation. This scenario presents a common challenge in network design where a proposed solution, while technically feasible, may not align with the overarching business objectives or the regulatory environment governing telecommunication services. The core of the challenge lies in balancing technical elegance with practical, compliant, and cost-effective implementation. Professionals must demonstrate an understanding that technology deployment is not an isolated technical exercise, but is deeply intertwined with business strategy, operational efficiency, and adherence to established frameworks. The correct approach represents best professional practice because it prioritizes a holistic evaluation that extends beyond mere technical performance. It acknowledges that the Alcatel Lucent multi-protocol label switching, MPLS, implementation must serve a defined business purpose and operate within the established regulatory landscape. Specifically, in the context of the 4A0-103 exam, which implicitly assumes a framework of responsible network deployment, this approach ensures that the chosen MPLS solution is not only technically sound, but also economically viable and compliant with any relevant service provider regulations or industry best practices that might be implied by the exam's scope. This aligns with the professional obligation to deliver solutions that are sustainable, ethical, and contribute positively to the organization's goals. An incorrect approach that focuses solely on the lowest initial capital expenditure without considering long-term operational costs, scalability, or potential regulatory compliance issues would be professionally unacceptable. This failure stems from a myopic view that neglects the total cost of ownership and the potential for future operational burdens or penalties. Another incorrect approach that prioritizes the most advanced, feature-rich MPLS solution without a clear business justification or a thorough assessment of its necessity and integration complexity would also be flawed. This demonstrates a lack of strategic alignment and potentially leads to over-engineering, increased operational overhead, and a failure to meet the actual business requirements. A third incorrect approach that overlooks the potential impact on existing network services or the complexity of integration with legacy systems without a proper risk assessment would be a significant professional failing. This indicates a disregard for operational stability and a failure to conduct due diligence in understanding the broader network ecosystem. Professional decision-making in such situations requires a structured process. First, clearly define the business objectives and the problem the MPLS solution is intended to solve. Second, identify all potential technical solutions and their associated costs, both capital and operational, benefits and risks. Third, critically evaluate each solution against the defined business objectives, considering scalability, security, manageability, and importantly, compliance with any applicable regulatory frameworks or industry standards relevant to the exam's jurisdiction. Finally, select the solution that offers the optimal balance of technical merit, economic feasibility, and regulatory compliance, ensuring a robust and sustainable deployment. Question 3. The control framework reveals that the network operator is evaluating strategies for managing label distribution protocol, LDP, sessions across various network segments, considering the need for both network stability and efficient resource utilization. Which of the following approaches to LDP session management best aligns with professional best practices for an Alcatel Lucent MPLS deployment? Option A. Universally disable LDP session protection across the entire network to minimize control plane overhead. Option B. Enable LDP session protection on every single link within the network to maximize session resilience. Option C. Enable LDP session protection on all critical links and selectively disable it on less critical links where transient session interruptions are deemed acceptable. Option D. Implement LDP session protection only on links that are part of a redundant path, ignoring single-homed critical links. The correct answer is C. Enable LDP session protection on all critical links and selectively disable it on less critical links where transient session interruptions are deemed acceptable. Explanation. The control framework reveals a critical juncture in network management where the efficient and reliable operation of multi-protocol label switching, MPLS, is paramount. The scenario presents a challenge in selecting the most appropriate method for managing label distribution protocol, LDP sessions, directly impacting network stability and service delivery. The professional challenge lies in balancing the need for robust control plane, signaling with the potential for resource overhead and complexity. Careful judgment is required to ensure that the chosen LDP session management strategy aligns with best practices for scalability, security, and operational efficiency within the Alcatel Lucent MPLS environment. Adhering to the principles outlined in the 4A0-103 syllabus, the correct approach, which involves judiciously enabling LDP session protection for critical links while allowing for more dynamic session establishment on less sensitive paths, represents best professional practice. This strategy leverages the benefits of LDP session protection, enhanced stability and resilience against transient network issues where it is most needed, thereby safeguarding core services. Simultaneously, it avoids unnecessary overhead on less critical links, optimizing resource utilization. This balanced approach demonstrates an understanding of the trade-offs inherent in network control plane design and aligns with the objective of building resilient and efficient networks, a core tenet of professional network engineering. An incorrect approach would be to universally disable LDP session protection across the entire network. This failure would represent a significant regulatory and ethical lapse by neglecting the responsibility to ensure network stability and service continuity. Such a decision could lead to widespread service disruptions if transient link failures occur, directly contravening the implicit obligation to provide reliable network services. Another incorrect approach would be to enable LDP session protection on every single link without considering the resource implications. This would be professionally unsound, as it could lead to excessive control plane overhead, potentially impacting overall network performance and scalability, demonstrating a lack of nuanced understanding of network design principles. A third incorrect approach might involve relying solely on alternative control plane mechanisms without adequately understanding their interaction with LDP, leading to unforeseen conflicts and instability. The professional reasoning process for similar situations should involve a thorough assessment of network topology, link criticality, and potential failure modes. Professionals must evaluate the benefits and drawbacks of different control plane configurations against the specific requirements of the services being carried. This includes understanding the impact on scalability, security, and operational manageability. A systematic approach, involving risk assessment and performance modeling, is crucial before implementing any significant changes to the network control plane. Adherence to vendor best practices and internal operational guidelines, as implicitly covered by the 4A0-103 syllabus, is also a critical component of professional decision-making. Question 4. The evaluation methodology shows that the current MPLS traffic processing is experiencing intermittent latency spikes during peak hours, impacting user experience. To address this, a network engineer is considering several approaches to optimize the process. Which approach best aligns with a controlled and effective methodology for network process optimization? Option A. Focus on increasing router hardware capacity across the network to handle the peak load, assuming the current software configuration is already optimal. Option B. Temporarily disable advanced MPLS features that are suspected of contributing to latency without investigating their specific impact or necessity. Option C. Implement immediate system-wide configuration changes to all MPLS routers based on a theoretical best practice for traffic shaping, without prior testing. Option D. Conduct a detailed analysis of traffic patterns and router performance metrics. Develop a targeted optimization strategy, test it in a lab environment, and then deploy it in a phased manner with rollback capabilities. The correct answer is C. Implement immediate, system-wide configuration changes to all MPLS routers based on a theoretical best practice for traffic shaping, without prior testing. Explanation. This scenario presents a professional challenge in network operations, where the efficient processing of MPLS traffic is paramount for service delivery. The challenge lies in balancing the immediate need for performance optimization with the long-term implications of configuration changes, particularly concerning the potential impact on network stability and adherence to established operational procedures. Careful judgment is required to select an approach that not only improves performance, but also aligns with best practices for network management and any applicable regulatory guidelines for service assurance. The correct approach represents best professional practice because it prioritizes a systematic and controlled method for process optimization. This involves thorough analysis, testing in a controlled environment, and phased deployment. Such a methodology minimizes the risk of unintended consequences, such as service disruptions or performance degradation, which could have regulatory implications if they violate service-level agreements, SLAs, or impact critical infrastructure. Adhering to a structured change management process ensures that all optimizations are documented, auditable, and reversible, which is crucial for compliance and troubleshooting. An incorrect approach that bypasses thorough testing and validation before implementation poses significant regulatory and ethical failures. It demonstrates a disregard for network stability and the potential impact on end users, which can lead to breaches of contractual obligations, SLAs, and potentially violate regulations governing telecommunications service reliability. Implementing changes without proper risk assessment is professionally negligent. Another incorrect approach that focuses solely on immediate performance gains without considering the underlying causes or potential side effects fails to address the root of any inefficiencies. This can lead to a reactive rather than proactive network management strategy, increasing the likelihood of recurring issues and potentially violating the spirit of regulations that mandate robust and reliable network services. The professional decision-making process for similar situations should involve a clear understanding of the network's current state, the specific performance issue being addressed, and the potential impact of any proposed changes. This includes consulting network documentation, change management policies, and any relevant regulatory requirements. A risk assessment should be conducted, followed by the development of a detailed implementation plan that includes rollback procedures. Testing in a lab or staging environment is essential before deploying to production. Continuous monitoring post-implementation is also critical to validate the effectiveness of the changes and identify any unforeseen problems. Question 5. Investigation of a proposed MPLS network configuration change by an enterprise customer, aimed at reducing operational costs by simplifying label distribution protocols, raises concerns about potential impacts on traffic engineering and service convergence times. The network engineer must assess the stakeholder perspective of the enterprise customer, who relies on the MPLS network for critical, time-sensitive data transmission. What is the most professionally responsible approach to address this request? Option A. Immediately implement the proposed simplification to demonstrate responsiveness to the customer's cost-saving objective, assuming the impact on critical services will be negligible. Option B. Conduct a thorough technical analysis of the proposed simplification's impact on label distribution, traffic engineering, and convergence times, and then engage with the customer to present findings and collaboratively explore alternative solutions that balance cost reduction with service assurance. Option C. Proceed with the configuration change based on the customer's request, prioritizing immediate cost savings over potential unquantified network performance degradation. Option D. Inform the customer that MPLS label distribution protocols are complex and cannot be altered without significant risk, thereby rejecting the request outright without further investigation. The correct answer is B. Conduct a thorough technical analysis of the proposed simplification's impact on label distribution, traffic engineering, and convergence times, and then engage with the customer to present findings and collaboratively explore alternative solutions that balance cost reduction with service assurance. Explanation. This scenario presents a professional challenge due to the inherent conflict between a service provider's desire to offer competitive pricing and the regulatory obligation to ensure network stability and security. The stakeholder perspective of the enterprise customer is paramount, as they rely on the MPLS network for critical business operations. Misinterpreting or neglecting the implications of a proposed cost-saving measure on network performance and resilience can lead to service disruptions, financial losses for the customer, and reputational damage for the provider. Careful judgment is required to balance economic considerations with the contractual and regulatory commitments to service quality. The correct approach represents best professional practice because it prioritizes a thorough, risk-based assessment of the proposed configuration change. This involves understanding the specific impact on MPLS traffic engineering, label distribution, and forwarding equivalence class, FEC, convergence, by engaging with the customer to explain the potential risks and collaboratively seeking an alternative that meets both cost and performance objectives. The network engineer upholds the principles of transparency, due diligence, and customer-centric service delivery. This aligns with the spirit of regulatory frameworks that emphasize reliable and secure network operations, even if not explicitly detailed in the 4A0-103 syllabus itself, as the underlying principles of good engineering practice and customer service are universally expected. An incorrect approach that proceeds with the configuration change without adequate testing or customer consultation fails to uphold professional responsibility. This could be considered a regulatory failure if it leads to a breach of service-level agreements, SLAs, that are implicitly or explicitly governed by broader telecommunications regulations requiring service reliability. Ethically, it demonstrates a lack of due diligence and a disregard for the customer's business continuity. Another incorrect approach, which is to dismiss the customer's concerns outright without a technical evaluation, is professionally unacceptable. It signals a lack of customer engagement and a failure to understand the business impact of network decisions. This can lead to a breakdown in trust and a perception of unresponsiveness, potentially violating customer service expectations that are often a component of regulatory compliance in the telecommunications sector. A further incorrect approach, focusing solely on the immediate cost savings without considering the long-term operational implications, is short-sighted. This can lead to increased operational expenditure later due to troubleshooting, service restoration, and potential penalties for SLA breaches. It represents a failure to adopt a holistic, life-cycle approach to network management, which is a cornerstone of sound engineering and responsible service provision. The professional decision-making process for similar situations should involve a structured risk assessment. This includes identifying the proposed change, understanding its technical implications within the MPLS framework, e.g., impact on LDP RSVPT, traffic engineering databases, evaluating potential risks to service availability and performance, consulting with the customer to understand their business requirements and risk tolerance, exploring alternative solutions that mitigate risks, and documenting all decisions and their justifications. This systematic approach ensures that technical decisions are aligned with business needs and regulatory expectations. Question 6. What factors determine the optimal configuration of MPLS fast reroute FRR and redundant label switch paths LSB for an enterprise e-commerce platform to ensure business continuity and meet stringent service level agreements? Option A. The lowest initial capital expenditure for MPLS equipment and the ease of initial deployment without considering long-term operational costs or resilience. Option B, the availability of the latest MPLS hardware features and the potential for showcasing advanced network capabilities to the enterprise. Option C, the specific business impact of potential network outages on the enterprise's revenue streams and customer trust, alongside the regulatory requirements for network resilience and fault recovery time objectives. Option D, the preference of the network engineering team for implementing complex, manual failover procedures to demonstrate technical expertise. The correct answer is C, the specific business impact of potential network outages on the enterprise's revenue streams and customer trust, alongside the regulatory requirements for network resilience and fault recovery time objectives. Explanation. Scenario analysis. This scenario presents a professional challenge in network design and implementation where the primary stakeholders, a large enterprise with a critical e-commerce platform, business continuity is directly dependent on the reliability and performance of the MPLS network. The challenge lies in balancing the immediate cost-effectiveness of a proposed solution against the long-term risks associated with potential service disruption. The need for robust fault tolerance and rapid recovery mechanisms is paramount, as downtime directly translates to significant financial losses and reputational damage. Careful judgment is required to ensure the chosen MPLS configuration adequately addresses these business imperatives within the defined regulatory and operational constraints. Correct approach analysis. The correct approach prioritizes the implementation of robust MPLS resilience mechanisms, such as fast reroute FRR and redundant label switch paths, LSB, to ensure minimal service disruption in the event of link or node failures. This aligns with the overarching regulatory expectation of service providers to deliver reliable and resilient network services, particularly for critical infrastructure and enterprise customers. From a stakeholder perspective, this approach directly addresses the business need for high availability and rapid recovery, thereby safeguarding revenue streams and customer trust. The proactive investment in resilience is a demonstration of due diligence and adherence to best practices in network engineering, minimizing potential liabilities and regulatory scrutiny related to service outages. Incorrect approaches analysis. An approach that focuses solely on minimizing initial capital expenditure by deploying a basic MPLS configuration without adequate redundancy mechanisms is professionally unacceptable. This would represent a failure to adequately assess and mitigate business risks, potentially violating implicit or explicit service level agreements, SLAs, and failing to meet the stakeholders' fundamental requirement for business continuity. From a regulatory standpoint, such an approach could be seen as negligent if it leads to predictable service failures, potentially incurring penalties or sanctions, depending on the specific regulatory framework governing telecommunications services. Another incorrect approach would be to prioritize a technically complex but unproven MPLS feature solely for its novelty, without a clear demonstration of its benefit to the stakeholders' specific resilience requirements or its operational manageability. This demonstrates a lack of stakeholder focus and a potential for introducing unforeseen operational issues or security vulnerabilities, which could lead to service degradation or outages. This deviates from professional responsibility to deliver solutions that are both effective and practical for the intended business purpose. An approach that relies on manual intervention for fault recovery, even if technically feasible, is also professionally flawed in this context. The expectation for critical e-commerce platforms is near-instantaneous recovery. Manual intervention introduces significant delays, increasing the duration and impact of any service disruption. This fails to meet the stakeholders' implicit requirement for automated and rapid fault resolution, leading to unacceptable downtime and potential regulatory noncompliance with SLA commitments. Professional reasoning. Professionals should adopt a risk-based decision-making framework. This involves thoroughly understanding the stakeholders' business objectives, critical services, and tolerance for downtime. A comprehensive assessment of potential network failure points and their business impact is essential. The selection of MPLS features and configurations should be driven by the ability to meet these identified resilience and performance requirements. Professionals must then evaluate the cost-benefit of different solutions, always prioritizing the stakeholders' business continuity and regulatory compliance. Regular review and validation of the network's resilience against evolving threats and business needs are also critical components of professional practice. Question 7. When evaluating the implementation of a new MPLS VPN service requiring robust traffic engineering, which approach best ensures service stability and efficient resource utilization while adhering to best practices for network design and deployment? Option A. Prioritize the immediate activation of the VPN service by disabling all LSP protection mechanisms and addressing traffic engineering concerns in a later maintenance window. Option B. Implement the default LSP protection mechanism provided by the Alcatel Lucent platform without extensive testing to expedite service activation. Option C. Deploy a highly complex, custom traffic engineering solution that promises optimal path selection but has not been fully validated for stability in a production environment. Option D. Select an LSP protection mechanism that offers rapid rerouting capabilities and conduct thorough pre-deployment testing to validate its effectiveness under various failure scenarios. Correct answer is D. Select an LSP protection mechanism that offers rapid rerouting capabilities and conduct thorough pre-deployment testing to validate its effectiveness under various failure scenarios. Explanation. This scenario presents a professional challenge because network engineers are tasked with implementing a new MPLS VPN service that requires careful consideration of traffic engineering parameters. The challenge lies in balancing the immediate need for service activation with the long-term implications of suboptimal configuration choices, particularly concerning the potential for network instability and inefficient resource utilization. Adhering to the Alcatel Lucent 4A0-103 syllabus, which emphasizes practical implementation and troubleshooting within the context of established networking principles, requires a decision-making process that prioritizes robust design over expediency. The correct approach represents best professional practice because it involves a systematic evaluation of traffic engineering options, specifically considering the impact of different label switched path, LSP, protection mechanisms on network resilience and performance. By choosing an LSP protection method that offers rapid rerouting and minimizes traffic disruption during link or node failures, the engineer ensures the stability and reliability of the MPLS VPN service. This aligns with the implicit regulatory expectation of providing a dependable service, as outlined in General Telecommunications Service Provision Guidelines that mandate a certain level of uptime and performance. The decision to proactively test and validate the chosen protection mechanism before full deployment further demonstrates due diligence and adherence to best practices for network service delivery. An incorrect approach that prioritizes speed over thoroughness by selecting a default or less robust LSP protection mechanism without adequate evaluation would be professionally unacceptable. This failure stems from a disregard for potential service degradation and an increased risk of network outages, which could lead to breaches of service level agreements, SLAs, and customer dissatisfaction. Ethically, it represents a failure to act in the best interest of the service provider and its customers by knowingly implementing a potentially less reliable solution. Another incorrect approach, such as implementing a complex traffic engineering solution without fully understanding its implications or without proper testing, would also be professionally unsound. This could lead to unforeseen network behavior, performance issues, and increased troubleshooting complexity, ultimately impacting service quality and potentially violating operational guidelines that emphasize controlled and predictable network changes. A professional decision-making process for similar situations should involve a structured approach. 1. Understand the requirements. Clearly define the service objectives, performance expectations, and resilience needs. 2. Evaluate options. Research and analyze available technical solutions, considering their pros and cons in relation to the requirements. 3. Risk assessment. Identify potential risks associated with each option and develop mitigation strategies. 4. Testing and validation. Implement a rigorous testing phase to confirm the chosen solution's effectiveness and stability. 5. Documentation and review. Thoroughly document the decision-making process and the implemented solution, and seek peer review where appropriate. This systematic process ensures that decisions are informed, risks are managed, and the implemented solution meets the required standards of performance and reliability. Question 8. Compliance review shows that a network administrator is tasked with ensuring that high-priority voice traffic receives guaranteed bandwidth and low latency across an MPLS backbone. The administrator is considering different methods to achieve this. Which approach best aligns with proactive MPLS traffic engineering principles for guaranteed CoS? Option A. Implementing dynamic routing protocols without integrating them with traffic engineering mechanisms. Option B. Manually configuring static LSPs for all potential traffic flows without a clear monitoring strategy. Option C. Configuring explicit label switched paths, LSP, using RSVPTE with defined bandwidth and hop count constraints. Option D. Relying solely on the default MPLS forwarding behavior without any specific traffic engineering configurations. The correct answer is C. Configuring explicit label switched paths, LSP, using RSVPTE with defined bandwidth and hop count constraints. Explanation. Scenario analysis. This scenario presents a professional challenge related to the implementation of MPLS traffic engineering within a network governed by specific Alcatel Lucent 4A0-103 exam guidelines. The challenge lies in balancing the need for efficient network resource utilization and guaranteed quality of service, CoS, for critical applications with the potential for introducing complexity and operational overhead. The decision-maker must navigate the trade-offs between proactive traffic engineering and reactive adjustments, considering the impact on network stability, performance, and adherence to the defined operational framework. The professional must exercise judgment in selecting the most appropriate method for managing traffic flow, ensuring it aligns with the exam's specific technical and procedural expectations. Correct approach analysis. The correct approach involves leveraging the capabilities of MPLS traffic engineering to proactively establish explicit label switch paths, LSP, based on predefined constraints and objectives. This method aligns with best professional practice by enabling predictable traffic routing, ensuring CoS guarantees for sensitive applications, and optimizing network resource utilization. Specifically, it demonstrates an understanding of how to implement RSVPTE for LSP establishment, allowing for the definition of bandwidth, hop count, and other constraints. This proactive stance minimizes the risk of congestion and service degradation, directly supporting the principles of robust network design and operation as implicitly expected within the 4A0-103 framework. It reflects a deep understanding of traffic engineering's role in achieving network performance objectives. Incorrect approaches analysis. One incorrect approach would be to solely rely on the default behavior of MPLS forwarding without any explicit traffic engineering configuration. This fails to address the need for CoS and efficient resource allocation, potentially leading to suboptimal performance and congestion for critical traffic. It represents a failure to apply fundamental traffic engineering principles expected in advanced MPLS deployments. Another incorrect approach would be to implement dynamic routing protocols without integrating them with traffic engineering mechanisms. While dynamic routing ensures reachability, it does not inherently provide the granular control over path selection and resource reservation required for guaranteed CoS. This approach neglects the specific capabilities of MPLS traffic engineering for performance optimization. A further incorrect approach would be to over-engineer the network by creating an excessive number of static LSPs without a clear justification or monitoring strategy. While static LSPs offer control, an unmanaged proliferation can lead to significant operational complexity, routing instability, and inefficient resource utilization, contradicting the goal of efficient network management. Professional reasoning. Professionals should employ a decision-making framework that prioritizes understanding the specific network requirements, including application CoS needs and traffic patterns. This should be followed by an evaluation of available MPLS traffic engineering tools and techniques, such as RSVPTE, to determine the most suitable method for achieving the desired outcomes. The process involves assessing the trade-offs between proactive and reactive approaches, considering operational complexity, and ensuring alignment with established network design principles and the specific guidelines of the 4A0-103 exam. A thorough understanding of the technology's capabilities and limitations is crucial for making informed decisions that optimize network performance and stability. Question 9. The performance metrics show a consistent increase in latency for specific traffic flows traversing an MPLS network, impacting a critical customer application. Network engineers are reviewing the situation to determine the most appropriate course of action, Which of the following approaches best addresses this issue while adhering to professional network operational standards? Option A. Proceed with replacing the core MPLS routers involved in the affected paths, as hardware failure is the most likely cause of performance degradation. Option B. Advise the customer that the latency is within acceptable network tolerances and no immediate action is required, pending further observation. Option C. Immediately reconfigure quality of service (QoS) policies across the entire MPLS network to prioritize all traffic, assuming a general congestion issue. Option D. Initiate a detailed analysis of the affected label switched paths (LSP), examining their configuration, QoS markings, and the health of the involved label switching routers (LSR) for any anomalies or congestion points. Correct answer is D. Initiate a detailed analysis of the affected label switched paths (LSP), examining their configuration, QoS markings, and the health of the involved label switching routers (LSR) for any anomalies or congestion points. Explanation: the performance metrics show a consistent increase in latency for specific traffic flows traversing an MPLS network. This scenario is professionally challenging because it directly impacts service-level agreements, SLAs, and customer satisfaction, potentially leading to financial penalties and reputational damage. The decision-making process must balance network stability, performance, and adherence to established operational procedures. The correct approach involves a systematic investigation of the MPLS path, focusing on potential bottlenecks or misconfigurations within the label switched paths (LSB) and their associated quality of service (QoS) policies. This aligns with best professional practice by prioritizing a data-driven, methodical troubleshooting process. It ensures that any remediation is targeted and effective, minimizing disruption to other network services. Adherence to operational guidelines and vendor best practices for Alcatel Lucent MPLS deployments is paramount. An incorrect approach would be to immediately implement broad, network-wide QoS policy changes without a thorough understanding of the root cause. This could inadvertently degrade performance for other services or introduce new issues, violating the principle of least privilege and potentially contravening operational change management procedures. Another incorrect approach would be to ignore the metrics, assuming they are transient or insignificant. This failure to act promptly on performance degradation is a direct violation of professional responsibility to maintain network integrity and meet SLA commitments. It also risks escalating the problem to a more severe outage. A third incorrect approach would be to solely focus on hardware replacement without diagnosing the underlying software or configuration issue. This is inefficient, costly, and fails to address the actual problem, demonstrating a lack of analytical rigor and adherence to systematic problem solving. Professionals should employ a decision-making framework that begins with clear problem identification and data gathering, performance metrics. This is followed by hypothesis generation and testing, prioritizing the most probable causes based on network topology, configuration, and known issues. Remediation should be planned, tested in a lab environment if possible, and implemented with rollback procedures. Continuous monitoring after remediation is crucial to confirm resolution. Question 10. The risk matrix shows a high probability of service degradation for critical financial transactions due to potential congestion on core network links during peak hours. The network utilizes Alcatel Lucent MPLS with RSVPTE capabilities. Which approach best mitigates this risk while adhering to operational best practices for MPLS traffic engineering? Option A. Increase the overall bandwidth of all core network links to accommodate potential peak hour traffic, assuming critical transactions will benefit from the increased capacity. Option B. Configure explicit LSPs using RSVPTE with defined bandwidth and administrative group constraints to prioritize and guarantee the required quality of service for financial transaction traffic. Option C. Rely on the default behavior of the IGP to route financial transaction traffic, assuming it will find the best available path during peak hours. Option D. Implement static LSPs for financial transaction traffic, ensuring they bypass potentially congested links without considering dynamic network conditions. The correct answer is B. Configure explicit LSPs using RSVPTE with defined bandwidth and administrative group constraints to prioritize and guarantee the required quality of service for financial transaction traffic. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent complexity of MPLS traffic engineering and the potential for misconfiguration to impact critical network services. The challenge lies in balancing the need for efficient resource utilization and performance optimization with the imperative to maintain network stability and adhere to service-level agreements, SLAs. A misjudgment in applying traffic engineering principles can lead to suboptimal performance, increased latency, packet loss, and ultimately, service degradation, which has direct implications for business operations and customer satisfaction. The pressure to implement changes quickly, while ensuring accuracy and compliance, adds to the difficulty. Correct approach analysis. The correct approach involves a thorough understanding of the Alcatel Lucent MPLS implementation and its specific traffic engineering capabilities, as detailed within the 4A0-103 syllabus. This includes leveraging features like constraint-based routing, CSBF, and RSVPTE to establish explicit label switched paths, LSB, that adhere to defined bandwidth hop count and administrative group constraints. The professional practice here is to meticulously plan the LSB configuration, considering the impact on existing traffic and potential congestion points. This approach aligns with best practices for network stability and performance, ensuring that traffic is routed along paths that meet its requirements without negatively impacting other services. It demonstrates a commitment to proactive network management and adherence to operational guidelines that prioritize service integrity. Incorrect approaches analysis. One incorrect approach would be to rely solely on default routing protocols without explicit traffic engineering for critical traffic. This fails to address the specific performance requirements of the high-priority data, potentially leading to it being routed over congested links or paths that do not meet its latency or bandwidth needs. This is a regulatory failure because it neglects the implicit requirement to meet service-level objectives and operational best practices for managing critical traffic, which are foundational to network reliability. Another incorrect approach would be to implement static LSBs without considering dynamic network conditions or the potential for link failures. While static LSBs offer predictability, they lack the resilience and adaptability of RSVPTE. If a link within a static LSB fails, traffic will be dropped until manual intervention occurs, violating the principle of network availability and potentially breaching SLAs. This represents an ethical failure as it prioritizes a simplistic configuration over the guaranteed service delivery expected by users. A third incorrect approach would be to over-provision bandwidth on all links indiscriminately as a workaround for poor traffic engineering. This is inefficient, costly, and does not guarantee that the critical traffic will actually utilize the provisioned bandwidth effectively. It fails to address the root cause of potential performance issues and demonstrates a lack of technical understanding of traffic engineering principles, which is a professional failing in network management. Professional reasoning. Professionals should adopt a systematic decision-making process that begins with a clear understanding of the traffic's requirements, bandwidth, latency, jitter. This should be followed by an assessment of the existing network topology and resource availability. The next step involves consulting the relevant documentation and training materials, such as those covered in 4A0-103, to identify the most appropriate MPLS traffic engineering tools and techniques. A pilot or simulation phase is crucial before full deployment to validate the configuration and its impact. Continuous monitoring and performance analysis post-implementation are essential for ongoing optimization and troubleshooting. This methodical approach ensures that decisions are data-driven, compliant with operational standards, and focused on achieving desired network outcomes. Question 11. Compliance review shows that a network engineer has observed intermittent packet loss and increased latency on several critical MPLS LSB paths. The engineer, without performing a detailed impact analysis or consulting existing traffic engineering policies, immediately implements new, more restrictive bandwidth constraints on the interfaces involved, believing this will alleviate congestion. What is the most appropriate course of action to address this situation, adhering to best practices for network operations and the implied regulatory framework of a professional Alcatel Lucent MPLS deployment? Option A. Proceed with the newly implemented restrictive bandwidth constraints, as they are intended to prevent congestion and monitor the network for further issues, assuming the problem will be resolved by this action. Option B. Document the observed performance degradation and assume it is a transient issue that will resolve itself without further intervention. Option C. Revert all recent configuration changes to default settings to ensure network stability, and then reevaluate the performance issues from a clean slate. Option D. Immediately revert the newly implemented restrictive bandwidth constraints and initiate a thorough diagnostic process to identify the root cause of the performance degradation, including analyzing current LSP states, traffic patterns, and potential misconfigurations before proposing any corrective actions. The correct answer is D. Immediately revert the newly implemented restrictive bandwidth constraints and initiate a thorough diagnostic process to identify the root cause of the performance degradation, including analyzing current LSP states, traffic patterns, and potential misconfigurations, before proposing any corrective actions. Explanation. This scenario presents a professional challenge due to the critical nature of MPLS traffic engineering in ensuring service-level agreements, SLAs, are met. The core difficulty lies in balancing network performance optimization with adherence to established operational procedures and the specific configuration guidelines mandated by Alcatel Lucent for the 4A0-103 exam context, which implicitly represents a controlled, best practice environment. Careful judgment is required to select an approach that is both technically sound and compliant with the implied regulatory framework of a professional networking environment. The correct approach represents best professional practice because it prioritizes a systematic, documented, and validated method for implementing changes that directly impact service delivery. This aligns with the principles of network governance and operational excellence, ensuring that any modification to traffic engineering policies is understood, tested, and approved before deployment. This methodical process minimizes the risk of service disruption, maintains network stability, and provides a clear audit trail for compliance and troubleshooting. The focus on understanding the impact on existing LSP paths and potential congestion points before making changes is paramount in a production environment. An incorrect approach that involves immediate, unverified implementation of new constraints without prior analysis fails to adhere to fundamental network operational best practices. This bypasses crucial validation steps, increasing the likelihood of unintended consequences such as LSP flapping, increased latency, or outright service outages. Such an action would be a direct violation of operational procedures designed to safeguard network stability and service continuity. Another incorrect approach, which is to revert to default configurations without understanding the root cause of the observed performance degradation, is also professionally unacceptable. While it might temporarily resolve an issue, it fails to address the underlying problem and could lead to recurring performance issues. It demonstrates a lack of analytical rigor and a failure to properly diagnose and resolve network anomalies, which is a core responsibility of a network engineer. A further incorrect approach, which is to ignore the observed performance degradation and assume it will self-resolve, represents a severe dereliction of duty. Network performance issues, if left unaddressed, can escalate and have significant business impact. This approach demonstrates a lack of proactivity and accountability, directly contravening the professional obligation to maintain network health and performance. The professional decision-making process for similar situations should involve a structured troubleshooting methodology. This typically includes 1. Clearly defining the problem and its impact. 2. Gathering relevant data, logs, performance metrics, configuration details. 3. Forming hypotheses about the root cause. 4. Testing hypotheses through controlled experiments or analysis. 5. Implementing solutions based on validated findings. And 6. Verifying the resolution and documenting the process. In the context of MPLS traffic engineering, this means thoroughly understanding the existing LSP configurations, the traffic patterns, and the potential impact of any proposed changes on the overall network. Question 12. The performance metrics show intermittent packet loss and increased latency on a critical customer-facing service that traverses an Alcatel Lucent MPLS network. Initial checks at the IP layer reveal no obvious routing instability or interface errors. What is the most appropriate next step to diagnose the root cause, considering the specific operational context of an Alcatel Lucent MPLS network as per the 4A0-103 framework? Option A. Immediately initiate a full packet capture on all affected customer edge interfaces to analyze individual packet behavior. Option B. Examine the status and health of label switch paths (LSB) and the label distribution protocol (LDP) adjacencies between the involved routers. Option C. Begin reconfiguring the quality of service (QoS) policies on the core interfaces to prioritize the affected service's traffic. Option D. Restart the MPLS service on all routers participating in the path of the affected service to clear any potential state issues. The correct answer is B. Examine the status and health of label switch paths (LSB) and the label distribution protocol (LDP) adjacencies between the involved routers. Explanation: this scenario presents a professional challenge in network operations where a critical service is experiencing intermittent performance degradation. The challenge lies in accurately diagnosing the root cause within the complex environment of MPLS, balancing the need for rapid resolution with the potential impact of troubleshooting actions on other services. The requirement to adhere strictly to the 4A0-103 Alcatel Lucent multi-protocol label switching framework means that any diagnostic and resolution steps must align with the principles and best practices outlined in that specific curriculum, which implicitly guides network engineers in their operational duties. The correct approach involves a systematic, layered investigation that prioritizes non-disruptive methods and leverages the specific diagnostic tools and methodologies relevant to MPLS as taught in the 4A0-103 curriculum. This includes examining MPLS-specific metrics such as label switching path, LSB status, label distribution protocol, LDP neighbor states, and traffic engineering, database consistency. By focusing on these elements, engineers can identify issues within the MPLS core without immediately impacting end-user traffic. This aligns with professional best practices by minimizing service disruption, ensuring data integrity, and adhering to the operational guidelines expected of a certified professional. The 4A0-103 framework emphasizes understanding the control plane and data plane interactions within MPLS, and a correct approach will reflect this understanding by first verifying the integrity of these interactions. An incorrect approach that immediately involves disabling or reconfiguring core MPLS interfaces without a clear, data-backed hypothesis would be professionally unacceptable. This could lead to widespread service outages, violating the implicit ethical obligation to maintain network stability and availability. Such an action demonstrates a lack of understanding of the interconnectedness of MPLS components and the potential cascading effects of drastic changes. Another incorrect approach might be to solely focus on Layer 2 or Layer 3 issues without considering the MPLS layer, failing to leverage the specific knowledge gained from the 4A0-103 certification. This would be a failure to apply the specialized expertise the certification represents, leading to an incomplete or inaccurate diagnosis. Furthermore, making changes based on anecdotal evidence or assumptions rather than concrete performance metrics and diagnostic data is a significant professional and ethical lapse, as it introduces unnecessary risk and can obscure the true problem. The professional decision-making process for similar situations should involve 1. Acknowledging the reported issue and its impact. 2. Reviewing available performance metrics and logs, specifically looking for MPLS-related anomalies. 3. Formulating a hypothesis based on the data, prioritizing hypotheses that can be tested with non-disruptive methods. 4. Executing diagnostic steps in a phased manner, starting with the least intrusive. 5. Documenting all findings and actions taken. 6. Escalating or seeking assistance if the problem persists or if more advanced troubleshooting is required, always referencing the principles learned in the 4A0-103 curriculum. Question 13. Compliance review shows that a large-scale enterprise MPLS network is experiencing suboptimal traffic distribution and occasional congestion on specific links, despite having a robust IGP. The network engineering team is considering implementing a traffic engineering solution to improve performance and resource utilization. They are debating between two primary approaches for explicit path control and traffic steering. Which of the following approaches, when implemented with careful consideration of network topology, service requirements, and operational capabilities, represents the most professionally sound decision for addressing the observed traffic engineering challenges? Option A. Deploying a resource reservation protocol traffic engineering (RSVPT) based solution to establish explicit paths with guaranteed bandwidth reservations for critical services. Option B. Implementing a segment routing (SR) based traffic engineering solution, leveraging its simplified control plane and efficient state management for scalable traffic steering. Option C. Implementing a combination of RSVPTE for core backbone services and segment routing for edge services, without a clear strategy for interdomain traffic engineering. Option D. Relying solely on the interior gateway protocol (IC) to manage traffic flow, assuming that optimal path selection will naturally occur with sufficient link metrics. The correct answer is B. Implementing a segment routing (SR) based traffic engineering solution, leveraging its simplified control plane and efficient state management for scalable traffic steering. Explanation. Scenario analysis. This scenario presents a challenge in network design and implementation, where a critical decision must be made regarding the appropriate method for traffic engineering within an MPLS network. The challenge lies in balancing the need for efficient traffic flow and resource utilization with the operational complexity and potential for misconfiguration. A misstep in selecting the traffic engineering mechanism can lead to suboptimal performance, increased latency, packet loss, and difficulties in troubleshooting, all of which have direct implications for service-level agreements, SLAs, and customer satisfaction. The professional must possess a deep understanding of the underlying protocols and their practical implications in a live network environment. Correct approach analysis. The correct approach involves selecting a traffic engineering mechanism that aligns with the specific requirements of the network and the services it supports, while adhering to best practices for MPLS deployment. In the context of the 4A0-103 exam, which focuses on Alcatel Lucent MPLS, this typically means understanding the capabilities and limitations of protocols like RSVPTE and segment routing. A well-justified choice would consider factors such as scalability, ease of management, convergence time, and compatibility with existing infrastructure. For instance, if the network requires explicit path control and preemption capabilities for critical services, RSVPTE might be the preferred choice. Conversely, for simpler, more scalable deployments, segment routing might be more appropriate. The professional decision-making process here involves a thorough assessment of network topology, traffic patterns, service requirements, and operational expertise. Incorrect approach is analysis. An incorrect approach would be to default to a single traffic engineering method without proper evaluation, or to implement a method that is overly complex for the network's needs, or, conversely, too simplistic to provide the required control. For example, choosing RSVPTE solely because it is a mature technology without considering the operational overhead and potential for state explosion in large networks would be a failure. Similarly, opting for segment routing without ensuring adequate understanding of its control plane mechanisms and potential for traffic steering issues could lead to unintended consequences. Another incorrect approach would be to ignore the need for traffic engineering altogether, relying solely on interior gateway protocol (IC) metrics, which often do not reflect actual link utilization or service priorities, leading to inefficient traffic distribution and potential congestion. Such choices demonstrate a lack of due diligence and a failure to apply the principles of sound network engineering as expected within the scope of the 4A0-103 certification. Professional reasoning. Professionals should approach traffic engineering decisions by first defining clear network objectives and service requirements. This involves understanding the types of traffic, their sensitivity to latency and jitter, and any specific SLA commitments. Subsequently, they must evaluate the available traffic engineering mechanisms, e.g., RSVPT segment routing, based on their technical merits, operational complexity, scalability, and compatibility with the existing network infrastructure. A comparative analysis, considering the trade-offs of each option, is crucial. This process should also involve consulting relevant Alcatel Lucent documentation and best practice guides pertinent to the 4A0-103 syllabus. Finally, the chosen solution should be validated through rigorous testing and simulation before deployment in a production environment. Question 14. Market research demonstrates that organizations are increasingly seeking to optimize network traffic flow for critical applications while managing operational complexity. Considering the Alcatel Lucent multi-protocol label switching (MPLS) Implementation, as per the 4A0-103 exam syllabus, which approach to defining forwarding equivalence classes. FEC best balances granular traffic engineering with control plane efficiency for a typical enterprise network environment. Option A, defining FECs based on specific UDP port numbers, allowing for fine-grained control over application-specific traffic flows. Option B, defining FECs based on individual IP addresses of end-user devices, providing the highest level of granularity for each host. Option C, defining FECs based on the source IP address of the traffic, enabling differentiated treatment based on originating network segments. Option D, defining FECs based on IP prefixes, allowing for efficient aggregation and traffic management based on destination networks. The correct answer is D, defining FECs based on IP prefixes, allowing for efficient aggregation and traffic management based on destination networks. Explanation. This scenario presents a professional challenge in network design and implementation, or the choice of MPLS forwarding equivalence class. FEC definition directly impacts network performance, scalability, and adherence to service-level agreements, SLAs. The challenge lies in balancing the granular control offered by a more specific FEC definition against the potential for increased control plane overhead and state management complexity. Careful judgment is required to select an FEC definition that aligns with business requirements and operational capabilities. The correct approach represents best professional practice because it prioritizes a FEC definition that is aligned with the specific traffic engineering requirements and the capabilities of the Alcatel Lucent platform, as per the 4A0-103 syllabus. By defining FECs based on IP prefix, the network can effectively manage traffic flows based on destination, enabling granular traffic engineering and ensuring that SLAs are met for different classes of service. This approach minimizes control plane overhead compared to more granular methods, while still providing sufficient flexibility for traffic management. It adheres to the principles of efficient resource utilization and predictable network behavior, which are implicitly expected within the regulatory framework governing telecommunications network design and operation, ensuring service continuity and quality. An incorrect approach that defines FECs based on individual IP addresses would lead to an unmanageable explosion of labels and control plane state. This would significantly degrade network performance due to excessive label switching, table lookups, and routing updates, making it impossible to meet typical SLA requirements for latency and throughput. Ethically and regulatorily, this would constitute a failure to provide a reliable and performant service, potentially violating service commitments and regulatory obligations for network availability and quality. Another incorrect approach that defines FECs based on the source IP address alone would fail to provide adequate traffic engineering capabilities for managing traffic based on destination, which is a primary driver for MPLS deployment in enterprise and service provider networks. This would result in suboptimal path selection and an inability to differentiate traffic based on its ultimate destination, leading to potential congestion and SLA breaches. This represents a failure in professional due diligence to design a network that meets the functional requirements of traffic management. A further incorrect approach that defines FECs based on the UDP port number would be overly granular for most network scenarios and would introduce significant control plane overhead, similar to the individual IP address approach. While it might offer very specific traffic control, it is generally not a practical or efficient method for defining FECs in an MPLS network for broad traffic engineering purposes. This approach demonstrates a lack of understanding of the practical trade-offs in FEC definition and would likely lead to an unstable and inefficient network, failing to meet professional standards for network design. The professional decision-making process for similar situations should involve a thorough understanding of the business requirements, the specific traffic patterns, and the capabilities of the deployed MPLS platform. A comparative analysis of different FEC definition strategies, considering their impact on control plane overhead, forwarding performance, and traffic engineering flexibility, is crucial. This analysis should be guided by the principles of network scalability, stability, and adherence to service-level objectives, ensuring that the chosen design is both technically sound and operationally viable within the relevant regulatory and ethical landscape. Question 15. The evaluation methodology shows that a network engineer is tasked with optimizing traffic flow across a critical MPLS backbone segment, experiencing intermittent congestion during peak hours. The engineer has identified several potential traffic engineering techniques to address this, but needs to select the most appropriate one for immediate implementation, while ensuring long-term network stability and adherence to service-level agreements. The engineer must consider the potential impact of link failures and the dynamic nature of traffic demands. Which of the following approaches best aligns with professional best practices for this scenario? Option A. Implement a dynamic traffic engineering solution that automatically reroutes traffic based on real-time link utilization and predicted traffic patterns, after a thorough simulation of failure scenarios and performance under various load conditions. Option B. Immediately deploy a static traffic engineering configuration that prioritizes the most critical traffic flows based on current observed congestion, without extensive analysis of alternative routes or failure impacts. Option C. Apply a complex, state-of-the-art traffic engineering protocol that has been recently introduced, assuming it will inherently resolve the congestion issues, without fully validating its compatibility with the existing network infrastructure or its performance under failure conditions. Option D. Focus solely on increasing link bandwidth on the congested segment, as this is the most straightforward solution to address immediate traffic overload, without considering the potential for traffic engineering to optimize existing resources. The correct answer is A. Implement a dynamic traffic engineering solution that automatically reroutes traffic based on real-time link utilization and predicted traffic patterns, after a thorough simulation of failure scenarios and performance under various load conditions. Explanation. This scenario presents a professional challenge in network design and implementation, where a critical decision regarding MPLS traffic engineering must be made under pressure, potentially impacting service-level agreements, SLAs, and network stability. The challenge lies in balancing immediate operational needs with long-term network resilience and adherence to established best practices, all within the context of the Alcatel Lucent 4A0-103 curriculum, which emphasizes practical application of MPLS principles. The correct approach, which involves a thorough analysis of traffic patterns and potential failure scenarios before implementing a specific traffic engineering technique, represents best professional practice. This aligns with the principles of robust network design and proactive risk management. By considering the implications of link failures and the dynamic nature of traffic, the engineer ensures that the chosen solution is not only effective in the short term, but also sustainable and resilient. This methodical approach minimizes the risk of service disruption and ensures compliance with the implicit regulatory expectation of providing reliable network services, as often stipulated in SLAs and industry standards, that the 4A0-103 exam prepares candidates to uphold. An incorrect approach that prioritizes a quick fix without adequate analysis poses significant regulatory and ethical failures. For instance, implementing a traffic engineering solution based solely on current, potentially transient, traffic conditions without considering future growth or failure modes could lead to network congestion or suboptimal routing. This failure to adequately plan and test could violate contractual obligations, SLAs, and demonstrate a lack of due diligence, which is an ethical failing in professional engineering. Another incorrect approach might involve applying a complex traffic engineering technique without fully understanding its implications or the specific network context, potentially leading to unintended consequences like routing loops or excessive control plane overhead. This demonstrates a lack of competence and a failure to uphold the professional standard of ensuring network stability and performance. The professional decision-making process for similar situations should involve a structured approach. 1. Understand the problem and its immediate impact. 2. Identify all potential solutions and their theoretical underpinnings within the relevant framework. In this case, MPLS traffic engineering as per 4A0-103. 3. Analyze the pros and cons of each solution, considering factors like complexity, scalability, resilience, and impact on existing services. 4. Evaluate each solution against established best practices and any applicable service level agreements or regulatory requirements. 5. Select the solution that offers the best balance of effectiveness, resilience, and compliance, and plan for thorough testing and validation. 6. Document the decision-making process and the rationale behind the chosen solution. Question 16. Risk assessment procedures indicate that a critical customer service relying on multi-protocol label switching, MPLS, is experiencing intermittent forwarding path instability. The network utilizes Alcatel Lucent equipment, and the configuration is managed according to principles covered in the 4A0-103 syllabus. To enhance stability and predictability of label distribution and forwarding, which of the following configuration approaches would best mitigate the identified risk while maintaining MPLS functionality for the service? Option A. Implement static label assignments for all traffic flows traversing the MPLS network. Option B. Configure label distribution protocol, LDP, to use targeted sessions between specific label switching routers, LSR, that are essential for the critical service path. Option C. Enable unsolicited LDP on all interfaces without any specific neighbor configuration or filtering. Option D. Disable LDP on all interfaces across the network to eliminate any potential for label-related issues. The correct answer is B. Configure label distribution protocol, LDP, to use targeted sessions between specific label switching routers, LSR, that are essential for the critical service path. Explanation. Scenario analysis. This scenario presents a professional challenge in network design and implementation, where a critical service relies on the stability and predictability of MPLS forwarding. The core difficulty lies in balancing the need for efficient traffic engineering with the potential for unforeseen network behavior that could impact service availability. The requirement to adhere strictly to Alcatel Lucent's 4A0-103 syllabus, which focuses on the technical intricacies of MPLS, means that any solution must be grounded in the principles and best practices outlined within that framework, without external or generalized regulatory interpretations. The professional challenge is to select a configuration that optimizes performance while mitigating risks, all within the defined technical scope. Correct approach analysis. The correct approach involves configuring the label distribution protocol, LDP, to operate in a controlled manner, specifically by utilizing LDP-targeted sessions. This method is best professional practice because it allows for explicit control over which label switching routers, LSR, exchange LDP information. By targeting specific neighbors, the network administrator can ensure that LDP bindings are only established between known and trusted peers. This granular control directly addresses the risk of unexpected label distribution or convergence issues that could arise from a fully dynamic, unsolicited LDP deployment across a large or complex network. Within the context of the 4A0-103 syllabus, this aligns with understanding LDP's operational modes and their implications for network stability and troubleshooting. It promotes a predictable forwarding plane by limiting the scope of LDP advertisements and ensuring that label bindings are established only where intended, thereby enhancing service resilience. Incorrect approaches analysis. One incorrect approach would be to disable LDP entirely on all interfaces. This is professionally unacceptable because it would prevent the establishment of any MPLS forwarding paths, rendering the MPLS network non-functional for the critical service. While it eliminates the risk of LDP-related issues, it does so by sacrificing the core functionality of MPLS, which is a direct failure to meet the service requirements. Another incorrect approach would be to enable unsolicited LDP on all interfaces without any form of filtering or targeted sessions. This is professionally unacceptable as it creates a broad attack surface for LDP-related instability. In a complex network, unsolicited LDP can lead to rapid and unpredictable label distribution changes, potentially causing flapping of forwarding paths and service disruption. This approach fails to implement best practices for LDP management as taught in the 4A0-103 syllabus, which emphasizes controlled and predictable label exchange. A third incorrect approach would be to rely solely on static label assignments for all traffic. While static labels offer predictability, they are highly inefficient and unscalable for managing dynamic MPLS networks. This approach is professionally unacceptable because it negates the benefits of dynamic label distribution protocols like LDP, making network management extremely cumbersome and prone to errors. It also fails to leverage the capabilities of MPLS as intended by the 4A0-103 syllabus, which covers dynamic label distribution mechanisms. Professional reasoning. Professionals facing such a scenario should first thoroughly understand the service requirements and the criticality of its MPLS-based transport. They should then consult the Alcatel Lucent 4A0-103 syllabus to identify the most appropriate MPLS features and configuration options for achieving stability and control. The decision-making process should prioritize solutions that offer granular control over label distribution and forwarding path establishment. This involves evaluating the trade-offs between dynamic and static configurations and understanding the implications of different LDP operational modes. A systematic approach, starting with a clear understanding of the problem and then applying knowledge from the specific technical framework, is crucial for selecting the most robust and reliable solution. Question 17. Cost-benefit analysis shows that implementing a new MPLS traffic engineering feature could significantly improve network utilization and reduce latency for critical applications, but it requires a substantial configuration change across multiple core routers. What is the most professionally responsible approach to introducing this feature? Option A. Implement the configuration changes directly across all core routers in the production environment during a scheduled maintenance window to realize the benefits as quickly as possible. Option B. Prioritize the cost savings identified in the analysis and proceed with the implementation across all core routers, assuming the benefits will outweigh any potential minor disruptions. Option C. Deploy the new feature only in a lab environment to validate its functionality, and then proceed with a full production deployment once lab testing is complete. Option D. Conduct thorough testing in a dedicated lab environment, followed by a pilot deployment on a small, non-critical segment of the production network, and then a phased rollout to the rest of the network with continuous monitoring and a rollback plan. The correct answer is D. Conduct thorough testing in a dedicated lab environment, followed by a pilot deployment on a small, non-critical segment of the production network, and then a phased rollout to the rest of the network with continuous monitoring and a rollback plan. Explanation. Scenario analysis. This scenario presents a common challenge in network engineering where a proposed network enhancement, while offering potential benefits, carries significant implications for network stability and operational efficiency. The core challenge lies in balancing the desire for improved performance and new features against the inherent risks of introducing changes into a live, production environment. The decision-maker must consider not only the technical merits, but also the potential impact on service availability, security, and compliance with operational guidelines. The absence of a clear, universally applicable best practice for such a decision necessitates a thorough, context-specific evaluation. Correct approach analysis. The correct approach emphasizes a phased, controlled deployment strategy. This aligns with best practices in network management and operational integrity, often implicitly or explicitly supported by regulatory frameworks that mandate service reliability and risk mitigation. By implementing the changes in a lab environment first, followed by a pilot deployment on a non-critical segment, and then a gradual rollout, the risks are systematically identified and managed. This methodology minimizes the potential for widespread disruption, allows for real-world validation of performance claims, and provides opportunities for rollback if unforeseen issues arise. This approach directly addresses the need for due diligence and risk management, which are fundamental to maintaining a stable and compliant network infrastructure. It reflects a professional commitment to minimizing service impact and ensuring the integrity of the network. Incorrect approaches analysis. Implementing the changes directly in the production environment without prior testing or a phased rollout is a significant regulatory and ethical failure. It demonstrates a disregard for service availability and customer impact, potentially violating service-level agreements, SLAs, and industry standards for network reliability. This approach prioritizes speed over safety and could lead to widespread outages, data loss, and reputational damage. Deploying the changes only in a lab environment without any form of pilot or staged production rollout is also professionally unsound. While it mitigates immediate production risk, it fails to validate the solution under real-world traffic conditions and operational constraints. This can lead to unexpected performance degradations or incompatibilities once the solution is eventually deployed, negating the initial benefit of lab testing and still posing a risk to the production network. Focusing solely on the cost savings without a thorough risk assessment and mitigation plan is a critical failure. Regulatory frameworks often require a comprehensive understanding of potential impacts, including operational and security risks, before implementing changes. This approach demonstrates a lack of professional responsibility and a failure to adhere to due diligence principles, potentially leading to noncompliance with operational mandates and increased long-term costs due to incident management and remediation. Professional reasoning. Professionals should adopt a structured decision-making process that begins with a clear understanding of the business and technical objectives. This should be followed by a comprehensive risk assessment, identifying potential impacts on service availability, security, and performance. A phased deployment strategy, incorporating lab testing, pilot programs, and gradual rollouts, should be the default approach for significant network changes. Continuous monitoring and a well-defined rollback plan are essential components of this process. Professionals must always prioritize service stability and customer impact, ensuring that any proposed changes are thoroughly validated and implemented in a manner that minimizes disruption and maintains compliance with relevant operational guidelines and regulatory expectations. Question 18. Benchmark analysis indicates that a financial trading application, critically dependent on low latency and high-throughput MPLS traffic-engineered paths, is experiencing intermittent performance degradation. The Service Level Agreement (SLA) mandates a maximum one-way latency of 5 milliseconds and a packet loss rate below 0.01%. The network engineer must ensure these parameters are consistently met. Given the Alcatel Lucent platform's capabilities, which approach best addresses this ongoing challenge? Option A. Implement static LSB configurations that are designed for average network conditions and do not incorporate any dynamic adjustment mechanisms, assuming the initial configuration is sufficient. Option B. Manually adjust the administrative weights of LSBs during peak hours based on anecdotal reports of congestion, without real-time performance data or a formal resignaling process. Option C. Rely on periodic manual checks using basic ping and traceroute commands to assess LSB health, assuming that if connectivity is present, the SLA is being met. Option D. Configure the MPLS traffic engineering (MPLSD) system to dynamically monitor LSB performance metrics such as latency and jitter. Upon detecting deviations that approach or exceed SLA thresholds, initiate automatic LSB resignaling or reoptimization to more optimal paths, adhering to established network policies. The correct answer is D. Configure the MPLS traffic engineering (MPLSD) system to dynamically monitor LSB performance metrics such as latency and jitter. Upon detecting deviations that approach or exceed SLA thresholds, initiate automatic LSB resignaling or reoptimization to more optimal paths, adhering to established network policies. Explanation. Scenario analysis. This scenario presents a common challenge in network engineering, where a critical service relies on the stability and predictable behavior of MPLS traffic engineering. The professional is tasked with optimizing label switch paths, LSB, to meet stringent service level agreements, SLAs, for a financial trading application. The challenge lies in balancing the need for low latency and high availability with the operational complexity of managing dynamic LSB adjustments. Misjudging the impact of LSB rerouting on other services or failing to adhere to established network policies can lead to service degradation, SLA breaches, and potential financial penalties. The need for a proactive, data-driven approach is paramount. Correct approach analysis. The correct approach involves leveraging the capabilities of the Alcatel Lucent platform to dynamically adjust LSB attributes based on real-time network conditions and predefined policies. This includes utilizing tools for monitoring LSB performance metrics such as latency, jitter, and packet loss. When these metrics approach or exceed predefined thresholds, the system should be configured to automatically initiate LSB resignaling or reoptimization. This process, often managed through MPLS traffic engineering extensions like RSVPTE, ensures that traffic is rerouted to less congested or more optimal paths, thereby maintaining service quality and adhering to SLAs. This aligns with best professional practices by prioritizing service continuity and performance through intelligent automation and adherence to network engineering principles. Incorrect approaches analysis. Manually adjusting LSB paths without a clear understanding of the real-time network state or the potential impact on other traffic is a significant regulatory and ethical failure. It introduces a high risk of unintended consequences, such as inadvertently rerouting critical traffic onto congested links or causing service disruptions. This approach lacks the systematic, data-driven methodology expected in professional network operations and can lead to SLA breaches, which may have contractual and regulatory implications. Implementing static LSP configurations that do not account for dynamic network changes is another failure. While seemingly simpler, it fails to address the inherent variability of network traffic and performance. This can lead to prolonged periods of suboptimal performance or outright service failures when network conditions change, directly violating the implicit or explicit requirement to maintain service quality as defined by SLAs. This demonstrates a lack of foresight and proactive network management. Relying solely on basic ping or traceroute for monitoring LSP health is insufficient. These tools provide a superficial view of connectivity and do not offer the granular performance metrics, latency, jitter, packet loss, necessary for effective traffic engineering and SLA adherence. This approach is reactive rather than proactive and fails to provide the data needed for informed decision-making, increasing the likelihood of service degradation and SLA breaches. Professional reasoning. Professionals in this domain must adopt a systematic, data-driven approach to network management. This involves understanding the specific capabilities of the Alcatel Lucent platform and the underlying MPLS protocols. A robust decision-making process would include 1. Defining clear performance objectives and SLAs for critical services. 2. Implementing comprehensive network monitoring that captures relevant performance metrics for LSPs. 3. Configuring automated mechanisms for LSP optimization and resignaling based on predefined thresholds and policies. 4. Regularly reviewing performance data and adjusting configurations as needed. 5. Maintaining thorough documentation of all configurations and operational procedures. This structured approach ensures that network resources are utilized efficiently, service quality is maintained, and potential issues are addressed proactively, thereby minimizing risks and ensuring compliance with operational standards. Question 19. Benchmark analysis indicates that a telecommunications provider is planning to deploy a new MPLS VPN service for enterprise clients. To ensure regulatory compliance within the specified jurisdiction, what is the most critical step to undertake during the planning and design phase of this deployment? Option A. Conduct a detailed review of the proposed MPLS VPN design and configuration against all applicable security and data privacy regulations, ensuring all mandated controls are incorporated. Option B. Rely exclusively on the vendor's documentation to confirm that the MPLS VPN solution meets all relevant regulatory standards without independent verification. Option C. Assume that the standard MPLS VPN features offered by the chosen vendor will automatically satisfy all regulatory compliance requirements. Option D. Postpone the detailed security and compliance review until after the MPLS VPN service has been fully deployed and is operational. The correct answer is A. Conduct a detailed review of the proposed MPLS VPN design and configuration against all applicable security and data privacy regulations, ensuring all mandated controls are incorporated. Explanation. Scenario analysis. This scenario presents a professional challenge related to implementing a new MPLS VPN service in a regulated telecommunications environment. The core challenge lies in ensuring that the implementation adheres strictly to the regulatory framework governing network security and data privacy, as mandated by the relevant authorities. The pressure to deploy new services quickly can sometimes lead to overlooking critical compliance steps, making careful judgment and a thorough understanding of regulatory requirements paramount. The complexity of MPLS VPNs, involving multiple layers of encapsulation and routing, further amplifies the need for meticulous attention to detail in security configurations. Correct approach analysis. The correct approach involves a proactive and comprehensive review of the proposed MPLS VPN implementation against the specific security and data privacy regulations applicable within the exam's jurisdiction. This includes verifying that all security controls, such as encryption protocols, access control lists, and traffic segregation mechanisms, meet or exceed the mandated standards. It also necessitates ensuring that the design incorporates mechanisms for logging and auditing network activity to comply with data breach notification and incident response requirements. This approach represents best professional practice because it prioritizes regulatory compliance and risk mitigation, safeguarding both the organization and its customers from potential legal repercussions and reputational damage. Adherence to these regulations is not merely a procedural step, but a fundamental ethical obligation to protect sensitive data and maintain service integrity. Incorrect approaches analysis. One incorrect approach is to assume that standard MPLS VPN configurations inherently meet all regulatory requirements without specific verification. This fails to acknowledge that regulatory frameworks often have specific mandates regarding encryption strength, data handling, and audit trails that may not be addressed by default configurations. Regulatory or ethical failure here is negligence, leading to potential noncompliance and security vulnerabilities. Another incorrect approach is to defer the security and compliance review to a later stage, such as post-deployment or during the first audit. This is a significant regulatory and ethical failure as it introduces substantial risk. Compliance should be embedded in the design and implementation phases, not treated as an afterthought. Delaying this review can result in costly remediation efforts, service disruptions, and penalties for non-compliance. A third incorrect approach is to rely solely on vendor-provided security features without independently validating their effectiveness against the specific regulatory mandates. While vendors aim for security, their solutions must be assessed within the context of the applicable legal and regulatory landscape. The failure here is a lack of due diligence and an over-reliance on third-party assurances, which does not absolve the implementing entity of its compliance responsibilities. Professional reasoning. Professionals facing such a scenario should adopt a risk-based approach to compliance. This involves 1. Identifying all applicable regulations and guidelines relevant to MPLS VPN deployment and data handling. 2. Conducting a thorough gap analysis between the proposed implementation design and the regulatory requirements. 3. Prioritizing security and compliance controls based on the identified risks. 4. Integrating security and compliance checks into every phase of the project lifecycle, from design to deployment and ongoing operations. 5. Documenting all compliance-related decisions and actions for audit purposes. 6. Seeking expert advice when necessary to interpret complex regulatory requirements or technical security measures. Question 20. Process analysis reveals that a telecommunications provider is planning to deploy a new multi-protocol label switching MPLS service to enterprise customers. The project team is eager to launch the service quickly to meet market demand. Before activating the service, what is the most critical step to ensure regulatory compliance within the specified jurisdiction? Option A. Rely on the MPLS vendor's documentation and internal technical team's assessment that the service adheres to general industry standards for network security and performance. Option B. Proceed with service activation and address any potential regulatory concerns that may arise after the service is live, prioritizing rapid market entry. Option C. Assume that standard MPLS protocols inherently satisfy all regulatory requirements without the need for specific validation against local laws. Option D. Obtain explicit confirmation from the relevant regulatory authority, or conduct a comprehensive internal audit against all applicable regulations to ensure the MPLS service design and operational procedures meet all legal mandates. Correct answer is D. Obtain explicit confirmation from the relevant regulatory authority or conduct a comprehensive internal audit against all applicable regulations to ensure the MPLS service design and operational procedures meet all legal mandates. Explanation. Scenario analysis. This scenario presents a professional challenge in network deployment where a new MPLS service is being introduced. The core difficulty lies in ensuring that the implementation adheres strictly to the regulatory framework governing telecommunications services within the specified jurisdiction, which for this exam is assumed to be a framework that mandates specific operational and security standards for network services, akin to those found in regulated markets. The challenge is amplified by the need to balance rapid service deployment with the imperative of regulatory compliance, especially concerning data handling and service assurance. Misinterpreting or overlooking regulatory requirements can lead to significant penalties, service disruptions, and reputational damage. Correct approach analysis. The correct approach involves a proactive and documented engagement with the relevant regulatory body, or a thorough internal review against established regulatory guidelines prior to service activation. This ensures that all aspects of the MPLS service, including its operational parameters, security features, and data handling protocols, are aligned with legal mandates. Specifically, this would involve verifying that the chosen MPLS implementation supports necessary traffic segregation, adheres to data privacy regulations, if applicable to the service type, and meets any mandated service level objectives or reporting requirements. This approach represents best professional practice because it prioritizes compliance as a foundational element of service delivery, mitigating risks and demonstrating due diligence. It aligns with the ethical obligation to operate within the bounds of the law and to provide services that are both reliable and compliant. Incorrect approach is analysis. One incorrect approach is to proceed with service activation based solely on vendor best practices or internal technical assessments without explicit verification against the regulatory framework. This is professionally unacceptable because vendor best practices, while valuable, do not supersede legal requirements. Relying on them without regulatory validation can lead to noncompliance, potentially resulting in fines or service suspension. Another incorrect approach is to assume that standard MPLS features inherently meet all regulatory obligations without specific validation. This is a failure of due diligence. Regulatory frameworks often have specific nuances regarding data integrity, security, or service availability that may not be covered by generic MPLS capabilities. A failure to confirm this alignment is a direct regulatory and ethical lapse. A third incorrect approach is to delay regulatory review until after the service has been deployed and is operational, citing time-to-market pressures. This is a significant professional and regulatory failure. It demonstrates a disregard for legal obligations and places the organization at high risk of non-compliance penalties. It also undermines the principle of responsible network deployment, which mandates that legal and regulatory considerations are addressed upfront. Professional reasoning. Professionals tasked with deploying new network services must adopt a risk-based approach that integrates regulatory compliance from the outset. The decision-making process should involve 1. Identifying all applicable regulatory frameworks and guidelines relevant to the service being deployed. 2. Conducting a thorough gap analysis between the proposed service implementation and the identified regulatory requirements. 3. Engaging with legal and compliance departments and potentially the regulatory authority to seek clarification and pre-approval where necessary. 4. Documenting all compliance activities, reviews, and approvals. 5. Implementing the service only after all regulatory requirements have been met and documented. This systematic process ensures that technical decisions are informed by legal and ethical considerations, fostering a culture of compliance and responsible service delivery.